the world of quantum computing.
Sounds exciting.
It is. It really is. And, we only pick the coolest, cutting-edge research papers to deep dive into. And this one, well, this one is really pushing the boundaries.
It definitely caught my eye.
Yeah, we're talking about Majorana's zero modes, or MZMs, and how scientists might have just cracked the code to creating them in a way that's actually, well, doable.
Yeah, I was a little skeptical when I first saw the title, but after reading it, this new approach seems way more realistic than anything else out there.
Exactly. So much more experimentally feasible.
Right.
It's a game changer. And the paper we're looking at is, let me get this right, Dynamic Realization of Majorana's Zero Modes in Particle-Conserving Ladder.
That's the one, fresh off the Archive press?
Yep, just published on December 19th, 2024, so it's hot off the press.
Piping hot.
So before we get into the nitty-gritty, can you give us a quick breakdown of what Majorana zero modes actually are? For those of us who haven't dedicated our lives to quantum physics.
Okay, so in the simplest terms, MZMs are these weird quasiparticles.
Quasiparticles?
Yeah, they're not really particles in the traditional sense, but they kind of act like them, It's like, imagine a wave in the ocean.
Okay.
It's not a single water molecules, right? It's the collective behavior of tons of water molecules, and that's kind of what MZMs are like.
Interesting. So not a brand new particle, but a new, phenomenon?
Exactly. A new type of emergent behavior that pops up in certain quantum systems. And here's the kicker. They have some seriously bizarre properties that make them super interesting for quantum computing.
Okay, I'm all ears. What kind of bizarre properties are we talking about?
The one that gets everyone excited is this thing called non-abelian braiding.
Non-abelian braiding, catchy.
It is kind of a mouthful, right? But imagine you're braiding hair, like actual strands of hair.
I can picture it.
Now imagine, instead of hair, you're braiding these MZMs, and here's the mind-blowing part. The order in which you braid them actually changes the quantum state of the system.
Wait, so just by changing the braiding order, you change the entire quantum state?
Yeah, it's like magic, but quantum magic, and that's why everyone is so hyped about MZMs, because this braiding property, it opens the door to building topological quantum computers.
So it's the way they're braided that allows for computation? That's wild.
It is wild. It's completely different from how classical computers work, and that's why they're so exciting for solving problems that are just impossible for classical computers to even touch.
That's fascinating.
Yeah, and to add to that, these topological quantum computers, they're theorized to be way more robust than other types of quantum computers because the information is encoded in the topology of the braiding. It's like it's protected from errors.
Like a self-healing computer.
Exactly.
That's amazing, but I have to ask, if they're so amazing, why haven't we built a topological quantum computer yet? What was the roadblocks?
Well, the biggest hurdle has been actually creating these darn MZMs in the first place. And the old methods, they were kind of like forcing a square peg into a round hole.
Okay, I'm sensing an analogy coming.
They often relied on breaking a fundamental symmetry of nature called particle number conservation, which basically means you can't just create a particle out of thin air, you have to destroy another one up a process, and that's really, really hard to do experimentally.
So like a cosmic balancing act.
Right, and this is not research, it's like they finally found the round hole for the round peg.
I like that. So this new method, it sidesteps that whole particle number conservation issue.
It does, which is why it has so much potential. It proposes a way to create MZMs without breaking this fundamental symmetry, making it way more experimentally feasible.
Okay, so this optical-lattice experiment, can you break that down for us?
Sure. Imagine ultra-cold atoms, like chilled to almost absolutely zero, and they're trapped in this very specific configuration that resembles a ladder, with two legs.
I'm picturing it.
And each leg of a ladder represents a chain of these ultra-cold atoms, and that's our playing field.
Okay, ultra-cold atoms, ladder configuration. Got it.
Now, here's the magic trick. They use lasers to create these incredibly precise and rapid pulses that activate something called single particle hopping processes. And it's like shaking a container filled with different objects.
So the lasers are shaking things up.
Exactly. But in a very controlled way, the shaking, or the pulses of laser light in this case, rearrange the atoms in a very, very specific way that induces the conditions needed for the MZMs to pop into existence.
So they're basically using lasers to choreograph a microscopic dance of atoms.
Yeah, that's a great way to put it.
I'm loving this, but I have to ask about some of the terminology in the paper.
Hit me.
Bosonization techniques and topological superconducting phase.
Yes, the jargon of quantum physics. Don't worry, I'll break it down.
Please do, because my brain is starting to hurt.
Let's start with bosonization. It's basically a mathematical tool that physicists use to simplify the incredibly complex interactions between fermions, which are like the building blocks of matter, electrons and protons and all that. It's like finding a shortcut through a dense jungle instead of hacking your way through the undergrowth.
So less machete, more zipline.
Exactly, and it helps them predict the exact arrangement of atoms needed to make those MZMs appear.
So it's a theoretical tool to guide the experiment.
Exactly. And now for the topological superconducting phase, this is a special state of matter, a very special state, where those fragile MZMs are actually protected from disturbances. You see, they're incredibly sensitive. The slightest nudge can destroy them.
Oh, so they need a safe space.
Exactly. They need a safe space, and this topological superconducting phase is like a force field. It shields them from the chaos of the quantum world, allowing them to exist stably.
Wow, a quantum force field? That's awesome.
It is pretty cool, right?
It is. It's like science fiction meets reality.
Totally.
The paper also mentions something called, let me see, infinite matrix product states, or IMPS. What in the world are those?
So IMPS, that's a super powerful computational method for simulating quantum systems, especially those with tons of particles, like the ones we're talking about here.
Right, tons of ultra-cold atoms.
It allowed the researchers to basically test drive their idea in a virtual environment to see if it would actually work before they went through the trouble of setting up the actual experiment.
Like a simulation?
Exactly, like a super high-tech simulation. And the results were really promising. It showed that this new scheme for creating MZMs, it has real potential.
So it's like they built a virtual quantum playground and everything worked perfectly.
Pretty much. And that's a big deal because it gives them confidence that this crazy idea might actually work in the real world.
I'm already blown away and we're just getting started.
I know, right? This stuff it's mind-boggling.
It is, and I have a feeling it's only going to get more mind-boggling from here. But before we dive even deeper into this quantum rabbit hole, we're going to take a quick break.
Sounds good.
We'll be back in a flash to explore the challenges and implications of this groundbreaking research, so don't go anywhere.
We'll be right back.
Okay, so we're back, and I'm still kind of reeling from all this talk about lasers and ultra-cold atoms and quantum force fields.
Yeah, it's a lot to wrap your head around.
It really is, but before the break, you were just starting to touch on the challenges of actually setting up this experiment in the real world.
Right, yeah, so it's one thing to simulate it on a computer, but actually doing it, it's a whole other ballgame.
So what are we talking about here? What are the big hurdles?
Well, for starters, just keeping those ultra-cold atoms in that super precise ladder configuration, it's incredibly tricky. Like any little disturbance, even a stray photon, can mess up the whole system.
Oh, wow. So they need like a completely isolated environment.
Yeah, basically you need incredibly sophisticated laser cooling techniques, a vacuum that's practically a perfect void. I mean, think about it. It's like trying to build a house of cards in the middle of a hurricane.
That's a great analogy. So it's not just about the tech, it's about creating this perfect, pristine environment for these atoms to do their thing.
Exactly. And then there's the laser pulses themselves. Those have to be timed and shaped just right to induce that specific atomic rearrangement that we need for the MZMs to emerge.
It sounds like they're conducting a microscopic orchestra with lasers.
That's a good way to put it. It's like a high-stakes performance where every photon is a note and the atoms are the dancers.
Okay, so let's say, hypothetically, that they pull it off, they manage to create these MZMs in the lab. What happens next? How do we go from these weird quasiparticles to an actual working topological quantum computer?
That's the million-dollar question, isn't it? And this is where things get really, really interesting.
That ready.
So remember that non-abelian braiding we were talking about earlier?
Yeah, the hair braiding analogy?
That's the key. It's a key to using these MZMs for computation.
So how does that actually work?
Okay, so imagine you have multiple MZMs, and you start braiding them, like weaving a complex pattern with them.
Okay.
The order in which you braid them, that actually determines the computation.
Wait, so it's the sequence of the braiding that dictates what the computer does?
Exactly. It's not like classical computers where you're manipulating electrical signals. It's all about this intricate dance of MZMs.
That's mind-blowing, but also incredibly complex. How do you even begin to control that?
It is complex, but that complexity also brings a huge advantage, robustness. Remember that topological superconducting phase we talked about, that quantum force field?
Yeah.
That protection, it also extends to the quantum information that's encoded in the braiding. So these topological quantum computers, they're much less prone to errors, which is a huge problem with other types of quantum computers.
So it's like they're self-correcting. That's incredible.
It is. It's a game changer for quantum computing because errors have been one of the biggest roadblocks to building practical quantum computers and topological quantum computing. It offers a potential solution to that.
So all this talk about MZMs and braiding and quantum force fields, it's all very fascinating, but what does it actually mean for the real world? What kind of applications are we talking about?
The applications are, well, they're pretty much limitless. I mean, imagine a world where we can simulate complex molecules with atom-level precision that would revolutionize drug discovery, materials science.
Wow, so we're talking about like designer drugs, materials with properties we haven't even dreamt of yet?
Exactly. And that's just the tip of the iceberg. Think about financial modeling, artificial intelligence, cryptography.
Cryptography, that's a big one. You mentioned earlier that this could be used to break encryption codes. How would that work?
Right, so a lot of the encryption algorithms that we use today, they rely on the fact that it would take a classical computer an insane amount of time to factor large numbers. It's like a brute force approach to security.
Right.
But quantum computers, and especially these topological quantum computers, they could potentially factor those numbers much, much faster, which would render those encryption methods completely obsolete.
So this is kind of a double-edged sword. On one hand, it could revolutionize cybersecurity, but on the other hand, it could also make us incredibly vulnerable.
That's true. It's a reminder that with great power comes great responsibility. But on the flip side, topological quantum computers could also help us develop new encryption methods that are resistant to quantum attacks. So it's like a constant arms race.
So we're not just talking about breaking the old, we're talking about building the new.
Exactly. It's a whole new paradigm for cybersecurity. And it's just one example of the profound impact that topological quantum computing could have on our world.
This has been an incredible deep dive. I feel like I've learned so much, and I'm also just in awe of the ingenuity and the sheer brilliance of the scientists who are pushing the boundaries of what's possible.
It is truly remarkable. They're pioneers exploring uncharted territory.
And speaking of uncharted territory, this research, it's really just a starting point, a glimpse into a future that's full of possibilities. And I'm curious, what are the next steps? Where do we go from here?
Well, the first step is to see if this actually works in the real world. Can they actually build a system that creates these MZMs using this new method?
Right, so it's time to put the theory to the test.
Exactly. And if it works, if they can actually create and control these MZMs, then the real fun begins. Then we can start exploring all this amazing applications, the drug discovery, the materials science, the cryptography. It's a whole new world of possibilities.
It's almost too much to comprehend. It's like science fiction becoming reality right before our eyes.
It is, and that's what makes it so exciting. We're on the verge of a quantum revolution, and it's going to change everything.
Well said. And you know what? I think it's time for us to take another quick break just to let all of this sink in.
Good idea. I need a moment to process all this quantum awesomeness.
We'll be back in a flash to wrap things up and explore some of the bigger questions surrounding this groundbreaking research, so don't go anywhere. Okay, we're back and ready to wrap up this mind-blowing deep dive into the world of Majorana zero modes and topological quantum computing.
Yeah, I'm still processing everything we've talked about.
It's a lot, but let's try to recap, hit the highlights one more time.
Okay, sounds good.
So we started with this incredible research paper that proposes a totally new way to create these MZMs, a way that actually seems, well, possible.
Yeah, and the key difference is that it doesn't require breaking that fundamental symmetry of nature, the particle number conservation.
Right, which was a major roadblock with the old methods.
Exactly. This new method, it's much more elegant. It works with nature instead of against it.
And then we got into the nitty-gritty of these optical-lattice experiments where they use lasers to choreograph the movements of ultracold atoms.
Like atomic ballet.
It really is, and the goal is to arrange those atoms in just the right way so that those MVMs emerge.
And once you have those MZMs, the real magic starts, the non-abelian braiding.
Right, where the order in which you braid these quasiparticles actually dictates the computation.
It's like weaving a quantum tapestry.
I love that analogy, and the fact that this braiding is happening within that topological superconducting phase, that quantum force field, it means that the information is protected from errors.
Exactly, which is a huge deal for quantum computing. It's one of the biggest advantages of topological quantum computing.
Then we touched on the potential applications, and they're just mind-boggling.
Right, we're talking about revolutionizing medicine, materials science, cryptography, pretty much every field you can think of.
It's almost overwhelming to think about the possibilities, but it's also incredibly exciting, right?
It is. It's like we're standing on the cusp of a new era, and this research, it's a major step forward.
So what are the next steps? Where do we go from here?
Well, the obvious next step is to actually try this out in the lab to see if they can actually create these MZMs using this new method.
So time to put the theory to the test.
Exactly. It's time to move from the virtual world to the real world.
And if it works, if they can actually pull this off, what happens then?
Then the real fun begins. Then we can start exploring all those amazing applications we were talking about, the drug discovery, the materials science, the new forms of encryption. It's a whole new world of possibilities waiting to be unlocked.
It's like we've just scratched the surface and there's this vast, uncharted territory ahead of us.
That's the beauty of science. There's always more to discover, more to explore. And this research, it's just the beginning.
Well, I don't know about you, but I'm feeling incredibly inspired right now. The future is full of potential.
Me too. It's a good time to be alive, especially if you're interested in quantum physics.
Absolutely. And you know what? I think this is the perfect place to wrap up our deep dive.
Yeah, I think we've covered a lot of ground today.
We have, and I want to thank you for joining us on this incredible journey into the quantum realm.
It was my pleasure. Always happy to talk about this mind-blowing stuff.
And to all our listeners out there, thank you for tuning in. We hope you enjoyed this deep dive as much as we did.
And if you did, be sure to check out our next episode. We'll be exploring another cutting-edge research paper that's pushing the boundaries of science and technology.
Until then, keep questioning, keep exploring, and keep diving deep into the mysteries of the universe.